We sports. Oh yeah, no, guys.
What's number 2? Skeleton structure. Oh, 4 is wrong. Sorry. Add what? Lone pair looks like this or that. Okay, so it's a non-bonding pair. Okay. I like how you worded that. Andrew, did you fill in your bubble sheet in pen yesterday?
You don't need money. You don't need money. Don't worry.
Okay, it went through and it went. The machine, like, it makes a sound when it like corrects something, like when it types in like the letter C when you had an A or whatever. So anytime there's a mistake, you hear like bup, bup, or you hear bup, 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 right? When it goes through and they're all wrong, it just sounds like. And if you do a bubble sheet in pen, it doesn't work because it works by reflection, and the graphite is reflective of the light, and pen is not. So it just, you got them all wrong. Yeah, it was exciting. Yes. 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 I know they're metals, but just let it go. They bond covalently. They're kind of near the staircase, so they do kind of have some covalent bonding capabilities. Okay? It doesn't make me happy either because I don't like gray areas. I like things to be black and white, but they are kind of in a gray area. Okay? All right, so you will actually see both ionic and covalent bonding for like aluminum and beryllium, but chances of you seeing any of them are not very likely, okay? Who are our exceptions? Hydrogen and B, ball. And also period 3 and lower. But period 3 and lower are like if you need to, okay? What are the exception numbers? Hydrogen needs 2, beryllium needs 4, boron needs 6, and aluminum needs, wouldn't it be nice if it were 8, but it is 6. Okay, and if you need to, but only if you need to, period 3 and below can have 10 or 12. Okay? So count the valence electrons, draw the skeleton structure, add lone pairs until every non-exception atom has 8 electrons. What do we do in step 4? Count. Yes, count the electrons and check if it matches your original number. In step 5, we say if there are the correct number of electrons, then either you're done or if it's an ion, what do you need to do if it's an ion? Brackets, yes, and charge. If you watched the video I assigned. Oh yeah. I even put an @ so it should have given you a notification. It's okay. There's a reason that I'm also doing it again now, right? Because I knew there would be people who missed that. On the other hand, if you did it, you'll be like ahead of the game. So we're good. Okay. So if we have the correct number of electrons, we're done. Or if it's an ion, we draw brackets and charge. What if we have too many electrons? We're going to first erase lone pairs from the central atom. And second, we are going to turn lone pairs into double or triple bonds. There's actually another way to do this that doesn't involve like drawing all the electrons. It just involves using the valence electrons you have, and then you don't have to erase. But I find that when you do it this way, the number of lone pairs you erase is going to be the number of multiple bonds that are formed. And that is a helpful thing to be able to see, okay? If you're interested in seeing a different method of doing this, feel free. Anybody on the internet other than me will show you the other way. I only discovered this a couple of years ago, and I like it because it helps people not make mistakes when they're forming double bonds, okay? So if we have too many electrons, we erase lone pairs from the central atom, we turn lone pairs into double or triple bonds, and here's the thing, the number of lone pairs you erase is equal to the number of multiple bonds you have to form. And we will get to what happens if we have too few electrons, but not today. So I'm not going to bother writing it down today. Okay. We're going to start you out easy. ClO3. Oh, I should write it like this. When I write it like this, there is a tendency for people to think that that is a letter I. Yes? I don't know if you would think that, but many people in the past have thought that. They've thought it is carbon, iodine, oxygen. It absolutely is not. It is chlorine, okay? So when I type it, I've made sure that I've used fonts where the capital I has crossbars on it, okay? The AP exam uses Times New Roman, and it also has crossbars on the I. So you can tell that this is not an I because it doesn't have a bar on the top and a bar on the bottom. So just watch out for that and don't get like fooled into thinking you have carbon, iodine, oxygen. And when I write it like up here, I will usually do it like that to make it very obvious that that's a lowercase l. All right. So step number 1, yes. No worries. Yeah. It's okay because the lesson is being recorded. I actually got it started almost right on time today. Very exciting. Woo, I know. Usually I'm like, oops, sorry, lost the first few minutes. I forgot to start recording. So, step number 1, what are we finding in step number 1? Count the valence electrons. And there are many ways to do this. I'm going to show you a very methodical way of doing it so you can do it without making mistakes. Okay, so we have 1 chlorine and we have 3 oxygen. Okay, so that's 1 times. How many valence electrons does chlorine have, and how do you know? It's in group 17. Therefore, it has 7 valence electrons. Hopefully, that seems like second nature to you by now. Oxygen, we have 3 of them. How many valence electrons? 6, because it is in group 16. So we would have then 3 times 6 is 18 electrons. And this is kind of the point we got to last. Do you remember doing these last day, like when we actually learned something? Maybe a while ago? Okay. The only thing is that now we have a charge. If we have a negative charge, we need to add one extra electron. What if we had a positive charge? What would we do? We would take away an extra electron. So in this case, we've got 17 plus 8, 7 plus 18 is 25, plus 1 is 26 electrons. Is good? Okay. Now, after we have found the valence electrons, what do we do next? Make the skeleton structure. Okay. And who's going to go in the middle? It would be lovely if it were oxygen. This is one of the ones where you look at your structure and you say they wrote chlorine first. So chlorine is going to go in the middle. Usually it is the singleton that goes in the middle, okay? Now, chlorine can do this. It can go in the middle because it is in row 3 and lower. Fluorine would never be able to go in the middle because it is in row 2. What does row 2 lack that elements in row 3 have? Yeah, there's not that empty D subshell, right? If we're in row 3, there's no electrons in the 3D orbitals yet. So we can put chlorine in the middle. But fluorine has 2s and 2p. There's no empty 2D subshell because there's no such thing as a 2D subshell. So fluorine, with its structure that looks like this, can only form one bond, but chlorine, because it's got a little more flexibility because of that empty 2D subshell, it can form more than one bond. Okay? Chlorine will only form more than one bond, though, if it is in the middle. Okay? Yes. Yes, of course. Chlorine, bromine, and iodine can only form more than one bond if they are the central atom. Fluorine can only ever form one bond. Yes. No, it really happens. I mean, I think so anyway, to my best understanding. You're welcome. So fluorine can only ever have one bond. So let's put chlorine in the middle because it is our singleton. And we will now make the most symmetrical structure that we can. Okay, and we're going to, in Lewis structures, we arrange things like top, bottom, side, side. Okay, top, bottom, side, side. So there is our skeleton structure. What is step? What was that step? What is step 3? Yes. Add lone pairs. Does this oxygen here need lone pairs? Yes, how many? 3, where do they go? Around the outside, top and bottom and side. Does chlorine need any lone pairs? Yes, it needs one pair. Up here, that's going to give us 8 because each bond is 2 and each lone pair is also 2. So there's 2, 4, 6, 8. All the other oxygens are just like the first oxygen. They all also need this many electrons. There we go. Just let it go. Okay? We're going to let it go at this point. We'll talk other stuff maybe later on in the bonding section. Okay, yes. Well, not all the oxygens are. Oh yeah. Oh, we'll get to that. Yeah. Yeah. It's all good. Thank you. All right, and now we're going to do what? Now that we have our skeleton structure and we have our lone pairs, counting. Yes. Count and check. Okay, and again, you don't have to do it this way, but this can help you count accurately, stop you from making mistakes. I often will write that I have 3 lines, and then I have, each oxygen has 3 lone pairs, so that's 3, 6, 9, and then a pair on chlorine makes 10 lone pairs. So that's going to be 3 times 2 is 6. And 10 times 2 is 20. And that gives us 26 electrons. And then we go, okay, we have counted. Now we are going to check. What are we checking it with? We're checking back here. Look at that! Huzzah! Yes? And once we've done that, either we are done, right? Or if it's an ion, we need to write brackets and a charge. Are we an ion? Thank you very much. Okay, so we're going to draw our brackets and our charge on the outside, and there we are, we're done. Is good? All right. Are we ready for something a little fancier? Okay. NO3 minus. Do you want to do the first part on your own, at least up until the skeleton structure and throwing on the lone pairs? Do it. There's blank paper at the back if you want blank paper. Help yourself. Is it? Is it? You'll want a periodic table. It is number 7. Does it have 7 valence electrons? We put the least electronegative in the center. Do you guys have your skeleton structure? So the three most electronegative elements, just for reference, are nitrogen, oxygen, and fluorine. In terms of, they are the most electronegative. I feel like it is more, but we will get a table of electronegativity so you can take a look at it. Okay. Nineteen, 20, 21, 22, 23, 24. So have we successfully gotten 24 electrons and NOOO? What did we do next? We added the lone pair, so hopefully at some point you had a structure that looked like this. Did you have a structure that looked like this? Hooray! And what did you do next? There are too many, but let's just make sure that we know that there are 3 lines. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs. So there's 1 pair too many. What do you do next? We're going to erase 1 pair. So there's 1 pair too many. So we're going to erase 1 pair from the central atom. And I'm actually going to redraw the whole thing just so you can see that. Okay. In my answer key, I draw out each step separately so that you can see it. You don't have to do that. You can just be like, I'm going to erase it. Now they're gone. Okay, you do not have to redraw, but I will show the redrawing just so you can see it. Not every time, but sometimes, because we're first starting out, okay? So this pair is now gone. Yes? And now you look at that and you say, now N has how many electrons? 6 electrons. So when we erase 1 pair from the central atom, then we need to also move 1 pair of lone electrons into a bonding position. I could have said that better. I could have said turn 1 lone pair into a bonding pair. That would have been better. Also turn 1 lone pair into a bonding pair. So you look around and you're like, oh, there's lone pairs everywhere. Which one do I choose? Does it matter? No, it doesn't matter. I'm going to pick any pair that I want to. What if I picked this pair here? And I'm going to move it in here. I thought I picked black. No. So now we have the pair that has moved in. You can see I've drawn that one in red to make it look a little bit different, right? We have oxygen, which has now only 2 lone pairs, but that's okay because it also has 2 bonding pairs. So the oxygen has 2, 4, 6, 8 electrons. Yes? Okay. Nitrogen has how many bonds? 4. So how many electrons is that? 8. Is it happy? Yes. Are we done? I need what we're missing something. What's up? Does it have to be that one? Did I have to move it from the bottom one? No, I could have moved it from the side. And in fact, that brings us to our next point. Okay, so first of all, we need brackets and a charge. Okay, so brackets. And we need a charge, which is -1. However, it would also be equally possible to have a structure that looked like this, where we had the 2 lone pairs on the oxygen and 2 bonding pairs. That happened on the left-hand side instead. So far, so good. And then this one was the 3 lone pairs and a single bond, 3 lone pairs and a single bond. And we show arrows in between showing that it actually goes back and forth between those 2. So it like alternates. Okay. Is there another possibility? Yes. We have, if there are 3 and you are asked to show resonance structures, that's what they're called, you have to show all 3. Okay, I will write that down in just a moment. Yes. Oops, oops, oops. Ding, 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 that's no good. That look better? Yeah, okay, thank you, yes. They are, but the 3 bonds are actually different. Okay, so if you held one molecule still, if you held one molecule still and could just look at it, the electrons would sometimes spend time over here, they would sometimes spend time over here, and they would sometimes spend time down here. So they're moving around. Yes? So what would happen is, for this first one to turn into the second one, this pair of electrons would move in here, forming this bond. Yes? But that would mean that nitrogen would have 1, 2, 3, 4, 5 bonds, right? If we move that one in. So it can't have 5 bonds. So that means that we have to kick a pair out here. Yeah, yeah. And then for the next one, we would have maybe, you know, this pair then moves in here, right? And now nitrogen would have 5 bonds again, and that's no good. So this one has to get kicked out to here. Yeah. And so that's what's happening, sort of. Yes. It can be any electron pair, it doesn't matter. Usually the more symmetrical, the better. So it's kind of better to have like that than like that, but nobody's going to mark you wrong on a Lewis structure if you put them on the side and the bottom rather than the top and the bottom, because Lewis structures are a smashed two-dimensional representation of a 3D thing anyway, so they are already inaccurate. Yes? So if we make it more inaccurate by putting them like here and here instead of here and here, it's not a big deal. Yes. 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 And that's actually the actual truth behind it. We draw resonance structures, but those electrons actually smear themselves out over the three areas. So at any given time, if you took a picture of it, you would see 1/3 of that double bond in each place. Kind of like wave function. So it's all smeared out all over the place. Okay? So what we can do is if we stop thinking about lone pairs, but if you're asked to draw resonance structures, we pretend that, it's distinctly, structure A and then distinctly structure B and then distinctly structure C. But what's really happening is we have N and we have a semi-bond here, yes, and we have N and a semi-bond here, and we have N and a semi-bond here. And rather than being a single bond or a double bond, this is a 1 1/3 bond. Yeah, so I mean, that's what happens. At that point, it becomes really hard to draw your lone pairs because it's like, which one do you put the two lone pairs on? They're also doing their own little, smeared all over the atom kind of dance. Yeah, yeah. You can think of it as alternating. Yeah, yeah. So this has ramifications for things like the bond length, because if you have a single bond, right, you've got your nucleus and you've got 2 electrons in the middle and you've got your nucleus. You have, do you guys remember Coulomb's law? F is equal to K Q Q over R squared, or you can write Q1, Q2. Either way is fine. Charge 1, charge 2. And let's say that this is charge 2, this is 2 electrons. Yes? What does R stand for, by the way? Distance between the charges. So what if we were to change the number of electrons in between, and instead of having a single bond, right, with the attractive force between the nucleus and the electrons, like that, what if we had a double bond? Now we would have, what would happen to our force? Would it be the same, or would it be bigger, or would it be smaller? Pardon me? It would be doubled. Okay, so we went from having essentially like 2 ropes pulling to having 4 ropes pulling, if you want to think about it that way. That's not really an awesome analogy, but it's kind of like that. Okay, so what's going to happen is that this is going to be stronger, and this one is going to be weaker. And what that means also is if it is stronger, the bond enthalpy is higher. And for this one, the bond enthalpy is and if these are being pulled, if these two at the bottom here are being pulled more strongly, what's going to happen to the distance between the two nuclei? Yeah, the distance between the nuclei is going to become smaller as well. So that bond is going to be shorter. Okay, so a double bond is shorter than a single bond. Okay, so here we have due to the stronger attraction, the double bond pulls the nuclei closer. And therefore a double bond is shorter than a single bond. Yes. To a certain extent, there also then becomes repulsive forces between the two nuclei and repulsive forces between the electron clouds of each atom. So there's like a balance between those repulsive forces and the attractive forces so that you end up with a stable distance that's a balance of those attractions and repulsions. Yeah? So we know the bond enthalpy of a single bond is smaller than the bond enthalpy of a double bond. We know the length of a single bond is longer than the length of a double bond. And as it turns out, all these bonds in the nitrate ion are the same length and they have the same bond enthalpy, which tells you that it's not like if you snap the bonds at one instant in time, you've got a double bond in one of them and a single bond in the other one. What you really have is you really have that double bond spread out over the three areas. Okay, does that make sense? Cool. So you may be asked to draw resonance structures, in which case draw however many different places you can put the bonds. If you're not asked to draw resonance structures, if they just say draw a Lewis structure, a correct Lewis structure, you could just draw one of them. But I think it's pretty likely that if you have to draw, if there are resonance structures, you would be expected to draw them. Okay. Have I given you guys the actual worksheet that says Lewis structures worksheet? No, I don't think I have either. So what I'm going to do is I am going to print that for you. Okay. And while I do that, you guys are going to draw the Lewis structure for BeH2. Okay. BeH2. And secondly, I'm going to have you do O3. Okay. So do those while I print out the worksheet. I'll write them up here because I'm going to move that in a second. And if there's resonance structures, draw them. Okay, we're recording again? I think so, yes. Okay. So we are now going to do O3. because I think BeH2 is fine. BeH2 should just look like this, because Be is one of our exceptions that only needs 4. Yeah. O3.
So like, you have enough electrons to that like that compound synopsis.
Yeah.
So
Okay, so we've got these, and the easiest way to arrange them is just in a line. So there's our skeleton structure. We are now going to add lone pairs to everybody. Because remember, after your skeleton structure, you are going to just scatter lone pairs wildly about until everybody has 8 electrons. You will scatter them with wanton abandon. Ha. Unless, of course, they're an exception, which they aren't because they're all oxygen. And then 4, we are going to count and check. So we are going to look and we're going to say we have 2 lines and we have 1, 2, 3, 4, 5, 6, 7, 8 lone pairs. So that's 2 times 2 is 4 electrons, and 8 times 2 is 16 electrons. So we now have 20 electrons. How many do we have? Too many. How many too many? 2 too many, so that's going to be 1 pair too many, yes? So how many pairs will we erase from our structure? We will erase 1 pair. So if I was to erase this one, and from which atom do we erase it? The central one. So here it goes, bye-bye. And now we need to help out oxygen, because right now oxygen only has 2, 4, 6. Who can help oxygen out? One of the side oxygens. Does it matter which one? No. So we are going to take these electrons and we are going to move them in, which will then give us O with 2 lone pairs, a double bond, and then an O, and then an O, and a with a single bonded O with 3 lone pairs. Am I done? Not yet. What do I need to do? Yeah, I need to also draw the other, what do we call that? Starts with an R. Resonance structure? Resonance. Now, what does the word resonant mean? It means like if you hear a bell, it goes ding, 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 ding. It's like back and forth. So it resonates. So that's kind of like the back and forth between the structures. Yes, it's resonating. Yes, yes. That's a different, it means that, you know what, it's kind of in the same vein because it rings true with them. So it's that same, like you're on the same frequency, which is sort of like a resonating, yeah? And if it were me, I would box my final answer because I've got a lot of work there and I'm like, oh, that's kind of messy and I wouldn't know what my final answer is. And I'd be like, this is my final answer in a box. There we go. And I remember we put our double-headed arrow in between. So don't forget. Now, does everybody have the little rules of writing Lewis structures? Everyone has that? Yes. Okay, are we good then for the weekend? We're just gonna go home and practice. Next week we'll do odd numbers, we'll do multiple central atoms, and we'll do expanded octets, and then we'll be done. This is, here we go, hang on. You are going to do the ones that are boxed. Number 1, 4, 7, 13, 16, 19, 21, 24, 26, 29, 52, 55, 58. Or you can just box them. Okay, cool. Yes. Did anybody else not get one of those? You got one. Yes.
Let me, not earlier talk about higher.
Yes.
But like double blocks, is that important for the Lewis structures?
Not particularly, no.
Just like a side factor?
Yeah.
Okay.
Yeah. Oh, can I share a video with you guys? Okay. Because you're almost at a point where you can appreciate this. I'll show it again later in the year because we're missing half the people and it'll actually make, it'll do a little bit better a little bit later on. Okay. I'm like, you're not doing worse in this class, but all right, whatever. Whoa. Oh, maybe today's not a good day to do it. Maybe everyone's watching soccer.
A dot isn't the best way to try to sum up how electrons come and go. There's things of a matter field that follows an equation the direct road. Schrödinger part of the whole equation, which I'll see in some see when it expands. Now they move from editing with the proton to watch them start to dance. Hydrogen is like, oh proton, I feel your tug. Central potential, dipped out, pulling on me. But I'm not pulling deep. No, that would make uncertainty say, oh, electrons go too much. Slow down your pace and put that orbit on me. Come on now, follow my lead. Come on now, follow my lead. Orbitals take shape, they do. The stable states of the quantum rules. And when a quantum approaches two, they combine in the bonding. Because hydrogen has a rule. It's by nature as a true energy configuring a molecule. Atomic bonding. milk is filled up with hate. The higher feelings are spread of the beautiful flowers and middle families that come into play. Well, here's a carbon with 6C. This ain't up to Pixie, but we're gonna mix the methane today with hydrogen and psychoatoms. I feel your tug. Got my electrons plugged up, pulling on me. Someone else around me. I'll hybridized to sp3. Stay carbon, here's our touch. Spread out 109.47 degrees. Someone now follow our lead. Someone now follow our lead. Well, the closest shape they do, combining states of the quantum rules. Like when a shell goes sp2, we see the part of the bonding. And as widely as their purview, they spread out in the molecule. Looking at the ring, they hold it true. Aromatic bonding. Aromatic bonding. Aromatic bonding. Aromatic bonding. They hold it true. When else take the shape they do. Come on with me, baby, come on. 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 When else take the shape they do. Combining base of residues. Like a release, CHU. They're hydrogen bonding. Peptides make a chain and group. And in a plate sheets and screws. With the secondary links they fold and move. They're all over your body. Come on with me, baby. Come on with me, they're all over your body. Come on with me, baby. Come on with me, they're all over your body. Come on with me, baby. Come on with me, they're all over your body. You're a chemical machine, it's best you do. The molecules take the shape of you. Acapella science.
That's just drawing.
Yeah, let me grab a pen.
I made Victoria. I did too much practicing how to make them cations and not enough practicing analyze.
up as box yet. And I will have an answer for that posted as well. You can run and it's all good. Yes. Did I hold on? Let's see. Oh, because I forgot to draw this pair here. Yeah. No, that's me just being, brain fart. Yeah. No, you're good. You're good. I'm wrong.